Hello, my dear all students. I hope all of you are doing well. This is our 11th week of this semester, and in this week, we are going to know about numerical solution of differential equation, which is also called ODE method, where we discuss Taylor methods and Euler's method. Okay, now let's start. At first, I would like to talk about ODE system. In the field of engineering and science, we come across physical and natural phenomenon which is represented by mathematical models using differential equations. Like simple harmonic motion or equation of motion or deflection of beam, etc. are represented by differential equation. These types of differential equation are quite complex, solved by using by usual methods. So, differential equation also helps us to solve such type of cases so that we can be solved by numerically this source of equation. In numerical method, we don't proceed in the hope of finding a relation between uh, x and y, which are our variables. We find the numerical values of the dependent variable for certain values of independent variable. A general ordinary differential equation, which is ODE, of the first order and first degree is dy by dx equals to fxy with the initial condition y x naught equals to y naught. Now, the most common used method for numerical solution of differential equation are Taylor's method, Euler's method, modified Euler's method, and Runge-Kutta method. Okay, now in this lecture, I would like to discuss Taylor's method and Euler's method. At first, Taylor's method. For Taylor's series, we have an equation which is fx equals to fa plus x minus a f prime a, that means first order differentiation of f, then x minus a whole square divided by factorial 2 f double prime a, which is the second order differentiation of the main equation, that is f. In this way we will proceed and putting fx equals to yx and a equals to x naught and x equals to x naught plus h, and we get yn plus 1 equals to yn plus h y prime n prime pi plus h square factorial 2y double prime n prime, where single prime means first order differentiation, double prime means second order differentiation, and triple prime means third order differentiation. And we can proceed in this way, where h is the difference between two steps. Okay, there is an example given for you where you can see that dy by dx equals to 1 plus xy with the initial condition y0 equals to 2, then find out y 0.0 0.1 and y 0.2 by using Taylor's method. You have to given you have some things like a equation, initial value of y, and you have to find some certain points at some certain points by using Taylor's method. Okay, now from Taylor's series, we already know that the equation which is y n plus 1 equals to y n plus h y prime n plus h square factorial to y double prime n, and then so on. So at first we put n equals to 1, and we get y1 equals to y naught plus h y h y prime naught plus h square factorial to y naught double prime plus h cube factorial 3y naught triple prime, and so on. As our main equation is yn plus 1, and when we put n equals to 1, that means n equals to 0, that means y1, and we get n equals to 0 in this way. So we get our desired equation, where x0 equals to 0 and y0 equals to 2 and h equals to 0.1, which is already given in our question. Okay, the equation is dy by dx equals to 1 plus xy, and if we differentiate this, that means write in the y prime in this format, then we get the same things, that is 1 plus xy, and when we apply the second order differentiation on the same equation, we simply get y double prime equals to y plus xy prime, and we can find out y double prime, y triple prime in the same way. And when we put using our initial conditions in equation 2, 3, 4, 5, we can find out our we can get our we can get a single value for each equation, and then putting all these values in the main equation, that is y1 equals to y naught plus hy prime naught, and we get our desired result. And this is our first findings for the first value, that is y equals to 0.1. Now we have to find out our second value, which is y equals to 0.2, and for this we simplify the Taylor series, and we put all the values in the equation, and we already get y1 equals to 2.1104. So all the values that we have, and put in the equations, that is 2, 3, 4, 5, and we can get a single value, and when we put all these values in the Taylor series, we get our desired result. Okay, that's all by solving this method, that is Taylor's method. Now we have to find out the same equations, or solve the same equations by using Euler's method. And for Euler's method, we already have an equation which is yn plus 1 equals to yn plus h into f x n yn. Okay, and there is given an example which is dy by dx equals to 1 plus xy, and the initial value is 1 y0 equals to 2, and we have to find y equals to 0.1 and y equals to 0.2. Okay. By using Euler's method, we can solve this equation. At first, we consider the main equation, that is y dy by dx equals to 1 plus xy, and we just simplify this fxy in this format, as this is because our requirement. So we can write fxy equals to 1 plus xy, where x equals to x naught equals to 0, y naught equals to 0, and h equals to zero point 0.1 as per the given question. And from the Euler's method, if we consider Euler's formula equals to number one equation, and if we put n equals to 0, which is our required things in the question, then we can get y1 equals to 2.1. That means uh, y equals to zero point 0.1. When we put y equals to zero point 0.1, we get a 2.1. Now, for the next approximation, we consider x1 equals to x naught plus h. So x naught equals to 0 and h equals to zero point 0.1, which is already given in the equation. And so we get y1 equals to 2.1, and this is the cross checking, nothing else. Now putting n equals to 1 in our desired equation, and we can get y.2 equals to 2.221. Now this is a very simple method, and then now um, we have to find we in this lecture I would like to discuss another method, which is the modified Euler method, which is another solution of differential equation, or ODE method. Now let's start. For modified Euler method, we have to consider something like y1 equals to y0 plus hf x0 x0 y0. Instead of approximating fxy by fx0 y0, we approximate it by half fx0 y0 plus f1 xy, which is the average of the slopes of a tangent at the point corresponding to x equals to x0 and y equals to x equals to x0 and x equals to x1. By using Euler method, um, Euler method gives us more accurate results than the simple Euler methods. Um, Modified Euler method gives us a more accurate results than the simple Euler method. This method would be correct only if the function is linear. Okay. Formula for the modified Euler method is given here. You have to remember this for the math solving. Now go to our next slide, where you can see that an example is given for you, and find out the value at the point 1.1 and 1.2. Some things are given here, which is dy by dx plus y by x equals to 1 by x squared. We just simplify this and we get the nice equation. Okay, now if xy equals to 1 minus xy divided by x squared, we just get it from a simplified format, where we put x equals to 1, y not x not equals to 1, y not equals to 1, and h equals to 0 0.1. Okay, by Euler's method, or simplified Euler's method, we get um, y1 equals to y naught plus h f x naught y naught. And if x naught y naught, we simplified it and get the result from our simplified equation. We just put it in the equation. Now we can find out that y1 equals to what? Y1 equals to 1. And for modified Euler method, when we try to solve a modified Euler method, we can get 0.99587. Uh, from both solution, we can see that we can see that the equation is more complex and the um, equation we find different values for different initial values. This is slightly difficult, I think, for your understanding, but you have to try this so that you can differentiate whether the Euler method or modified Euler method, which one is better. As I said, as I already said that modified Euler method provides a better result and more accurate result than the Euler method. Thank you all, and I think this is a little bit a lengthy lecture, but I hope all of you enjoyed my lecture. And please try to join our live session so that you can understand better. Thank you all.